In this problem, we'll graph an absolute value inequality. So the problem is the absolute value of y subtract 2x is less than or equal to 3. And the first step is to isolate the absolute value, but in this case that's already done. So what we would be looking for is if there was a number right here, we would have to divide both sides by that number. Or if there was something added or subtracted right here, we would have to add or subtract it to the other side. But since the absolute value is isolated, we go ahead and we separate this problem into two different problems. So the left-hand route right here is now y subtract 2x is less than or equal to 3, and we chose an and because it's a less than symbol. So right here, this less than symbol correlates to this and. If it were a greater than, it would be an or. And the other inequality is y subtract 2x is greater than or equal to -3. Now two things happened over here. Notice we switched the inequality to a greater than, and we changed the sign on the right hand side. Now we're going to solve these inequalities and graph them separately, and then we'll shade the overlap. And we shade the overlap because it's an and. So I like this to be in the form y equals mx plus b. Now at this point we don't really care too much about the inequality because we're just graphing a boundary line. So I'm going to change that to an equals sign. So the first thing I'm going to do is add 2x to both sides, and I have y equals 2x plus 3. And that is going to be graphed in just a second. Let's do the same thing to this problem. We add 2x and we have y equals positive 2x minus 3. So now what we have is two boundary lines. So we will scoot the screen up a little bit here, and we're going to graph these boundary lines. So the first boundary line has a y-intercept of 3 and has a slope of 2 over 1. So we rise 2, run 1, put a dot, rise 2, run 1, put a dot. Now since this was a less than or equal to problem right here, it's going to be a solid boundary. So I can take my pencil and add a solid boundary. Boundary lines go on forever, so we put arrows. Now let's go ahead and graph the other boundary line. So it has a y-intercept of -3. So we go down 3 and we put a dot. Oops, let's try that again. Put a dot. Now it also has a slope of positive 2. So up 2 over 1, up 2 over 1, and it's a solid boundary. Oops. Pretend I ran through the point 0, -3. Now what we're going to do is we're going to decide if the shading is in the middle in here, or if the shading is the outsides. And what we're going to do to make that decision is we go back up here and we're going to test the point 0, 0 in the absolute value. And if that comes out true, then we shade the section that contains 0, 0. So in this case I do have 0 is less than or equal to 3, which is true. So what that means down here is this point right here where I shaded came out true, and that means everything in between those two boundary lines will work. Now If that point did not come out true, oops, right there, then you would shade the outside. And that's true for all absolute value inequality problems. You either shade the inside or the outside. The AND problems are shaded in the middle, and the OR problems are shaded on the outside. Next, we'll simplify radicals using the product and quotient rules. So in this problem, I have the square root of a quotient, square root of 50 over 49. And we will put the square root symbol over the 50 and the square root symbol over the 49. The square root of 50 can be separated into the square root of 25 over the square root of 2. And that's all divided by the square root of 49. 25 and 49 are perfect squares, so we now have 5 times the square root of 2 over 7. And that's the answer to that one. All right, let's do one more. So the next one we'll do is the cube root of x to the 5th over 8. And the quotient rule says that we can take the cube root of the numerator and the cube root of the denominator. On the top, it's helpful to picture this as x cubed times x squared, because we have a cube root right here, so we want the item underneath the radical grouped up into something raised to the 3. On the bottom, we know that the cube root of 8 is 2, but just to draw a parallel to the previous example, I can write 8 as 2 cubed, and then I got that cubed there and that cubed there, and it's going to become just a 2. So what I have now is, on the top, the cube root of x cubed times the cubed root of x squared, and that's the product rule. And on the bottom, I'm just going to go ahead and take the cube root of 2 cubed, which is 2. Now, on the top, the cube root of x cubed becomes just x, and the 2x squared, underneath the radical, there isn't enough of them to pull out another set. So in this case, we have to leave the x squared underneath the radical, and it's done. Next, we're going to practice evaluating rational exponents. So the first one we're going to do is open parenthesis -9 raised to the 1/2. Now remember, the bottom number is the root. So this can be changed to the square root of -9. But wait, we can't find the square root of -9 because that's not a real number. So at this point, we'll just stop and we'll write not real. Now after we learn complex numbers, we can write the answer, but at this point we just stop. And that becomes the answer. Now if we change the problem slightly, and instead we don't have parentheses, so now let's put -9 raised to the 1/2. Now in this case, the power of 1/2 is only on the 9, it's not on the 1/2, or excuse me, it's not on the negative. So what that means is the negative sits out there, and then I have the square root of 9. But that's a problem I can do because I know that the square root of 9 is 3, so the answer to this one is -3. The next problem we're going to do is also evaluating a rational exponent, but in this case I have 27 raised to the 2/3. Now remember, the bottom number is the root and the top number is the power. So we're going to change this into radical notation. So what we're going to do is do the cube root of 27, and then the power, remember the power here is 2, So after we do the cube root 27, we'll raise it to the second power. So the cube root of 27 is 3, and 3 squared is 9. And that's our answer. Now, notice, let's do this problem again right next to it. We could have done 27 raised to the 2/3. We could have done the power first, but that's not as much fun. Let's change that to a radical sign, because it makes me have to grab my calculator, because I don't know what 27 squared is, but when I do my calculator, it is 729. Ugh, but then I have to find the cube root of 729. And truthfully, on my calculator, to do that, I just change it back to 729 raised to the 1/3, which gives me the number 9, and it matches the answer I had by doing the root first. But by doing the root first, I didn't need to grab my calculator. So doing the root first will make the number get smaller, like it did here. I now have a 3. And then doing the power next will make them get bigger. Whereas if I do the power first, I get some big number that then I have to take the root of. And yeah, you get the same answer, but this route right here is easier. On this problem, we're going to evaluate a rational exponent. So this time, let's use the pencil. I have the number 4 raised to the negative 2. Oops, let me erase that. I have 4 raised to the negative 3/2. So the first thing I'm going to do is deal with that negative symbol right there. So when you have a negative exponent, what it does is it flips the base. So instead of having 4, I now have 1/4. But this is still raised to the 3/2, but now that's positive. Now, I could take the exponent 3/2 and I could put it on both the numerator and the denominator. But really that's not necessary, because 1 raised to the anything is still just 1. So what I have is 1 over 4 raised to the 3/2. Then, let's scoot that up. I'm going to do the square root of 4 first, and then I'll raise it to the power of 3. So remember, this number here is a root, and this number here is a power. And I want to do the root first because it makes the number get smaller. So the square root of 4 is 2, and I still need to cube it, so I cube it and I have 1/8. So let's go over that again. The 3 things that I had to do in the original problem, I had to take the reciprocal of the base because of the negative. That made it 1/4. And then I took the square root of 4, and that made it a 2 right here. And then I took the 3rd power and it turned it into an 8th. Now don't lose track of the 1 all along. You've got the 1 on top here, 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 and a common student mistake is just to drop the 1 and then they have the 8. In this problem, we're going to simplify rational expressions. First thing we're going to deal with in this problem is this negative exponent. What that's going to do is flip the base. Let's take the reciprocal. So now I'm going to have y to the 1/3 power over x squared. And instead of being raised to the negative 1/2, it's now raised to the positive 1/2. And that's because that's what a negative exponent does, is it flips the base. Now I'm going to use the power of a power right here. So a power of a power, these 2 things get multiplied, and then these 2 things get multiplied. So let me show all my work on that. First, the y to the 1/3 is going to get raised to the 1/2, and the x squared is going to get raised to the 1/2. And then the power of a power rule says that if you have a power of a power, they get multiplied. So I'm going to multiply 1/3 and 1/2, and I get 1/6. And likewise down here, I'm going to multiply 2/1 times 1/2, but that is just 2/2. And 2/2 simplifies to just 1. So what I get for an answer is y to the 1/6 over x. And that's the answer. In this problem, we're going to solve for x. And this is solving an equation with a rational exponent. So what we're going to do here, remember this one on the bottom is a root, and this one on the top is a power. And because we're solving an equation, we can do operations to both sides. So on the left-hand side, we're going to raise, let me say that again. On the left-hand side, we're going to raise it to the 3, and then because it's an equation, we do it also to the right-hand side. So x to the 2/3 equals 4. On the left, I raise it to the 3, and on the right, I raise it to a 3. Now, a power rule says that you multiply this power times this power. And remember, this is actually 3/1. Well, when I multiply, I would get 6/3, but it's easier to cancel the 3's. So what I have on the left now is just x squared. And you'll see in a minute, but I'm just going to leave this. Well, no, I take it back. 4 times 4 is 16, times 4 is 64. So I'll go ahead and write 64. And then all I have left to do is to deal with the power of 2. So the inverse operation of squaring is a square root. So we'll take the square root of both sides. And on the left, what we get is just x. And on the right, we get plus and minus 8. And remember, we get 2 solutions because we took an even root of both sides. And then if we had taken an odd root, for example, if this had been a cube root of both sides, you would not get the plus and minus. In this case, we get 2 solutions. Now, let's just do one more of those. And this time we'll make it a little bit, new problem, a little bit harder. We'll have w minus 1 raised to the negative 2/5 is equal to 4. Now in this problem I have 3 things I need to do before I'll have isolated the w minus 1. So I have a negative sign I need to deal with, I have a 5th root, and a 2nd power. So I like to deal with the negative sign first. So I'm going to change colors here just to be clear. So my work starts here in pink, and I'm going to raise both sides to -1. And what that does on the left hand side is the power of a power rule. So this is a power of a power, those get multiplied. So now I have w, let's do that in white, minus 1 raised to, instead of -2/5, it's now raised to a positive 2/5. And on the right hand side, remember a negative power is a reciprocal of that base, so it becomes 1/4. And now it's kind of like the last problem. I need to raise each side to the 5th power and then take the square root. So I'll do my work here again in a different color. Let's choose pink again. So I'm going to raise both sides to the 5th power. And on the left hand side, those cancel. And what I get is w minus 1 raised to the 2nd power. And on the right hand side, I get 1/4 to the 5th power, which is 1/1024. And then I still need to take the square root of both sides. So I take the square root of the left and the square root of the right. Don't forget the even root property is going to apply. On the left, those two things cancel. And I have w minus 1 is equal to plus or minus 1 over 32. Now I'm not quite done because I haven't solved for w. I still have that minus 1 over there. So let's add it to both sides. And what I get when I add it to the left is just w, and what I get when I add it to the right is 1 plus or minus 1 over 32. But there's no variables involved here, so I really need to go ahead and finish this problem because 1 and 1 over 32 can be added. So what I'm going to do is change the 1 into a 32 over 32. And then I'll do these problems separately. So the first one is 32, right here, 32 plus 1 all over 32. So that is 33 over 32. Oops. Ooh, let's erase that. And then the other one is the 32 minus 1, which is 31 over 32. And it's sufficient to write your answer with a comma. It's clear to the reader that you have two solutions to this problem. Okay. We're going to use the even root property to solve this equation. So I'm going to subtract 5 from both sides, and I have 2x squared equals negative 5. I'm going to divide 2 on both sides, and I have x squared equals negative 5 over 2. And then I'm going to take the square root of both sides. I'll show my work here in pink. And on the left-hand side, those cancel. And on the right-hand side, I have plus or minus the square root of negative 5 halves. Now, the even root property applies because I took an even root of both sides. And on the right-hand side, we're not simplified because there's still a negative under the radical, and there's still a square root of 2 on the bottom. So what we'll do is we'll first pull out the negative as a imaginary number, so that's an I. That's because of this negative right here. Now I still need to rationalize this denominator because I'm not allowed to leave a radical in the denominator. So let's move the screen up. Now what we're going to have is, by the quotient rule, this is the square root of 5 over the square root of 2. Don't lose that I, it's running around. And I'm going to change colors here. Now I have a pink, and I'm going to multiply top and bottom by the square root of 1, excuse me, square root of 2. And remember, I'm allowed to do that because this pink box right here, that's just the number 1. You're allowed to multiply anything by the number 1. So on the left, I still have the x equals, oh, let's change to white. And on the right, I still have the plus or minus. And on the top, you have the square root of 5 times the square root of 2. And by the product rule, you can put those under the same radical. And it becomes square root of 10 on top. And I'll show that in a minute. And on the bottom, I have the square root of 2 times the square root of 2, which becomes the square root of 4. Now don't forget your I. Let's scroll the screen up. So on the left-hand side, I'll have the x. On the right-hand side, I have the plus or minus square root of 10 over, now square root of 4 is 2. Now that's rational. That's why we did that, because we had to rationalize the denominator. Here, this number right here, square root of 2, is not rational. And we're not allowed to leave an irrational number on the bottom. Don't ask why. That's irrational. But we're allowed to leave a 2 on the bottom. Oh, don't forget the I. Now we can box our answer in. This is the answer. X equals plus or minus square root of 10 over 2I. And it's sufficient to leave that as plus or minus, although you'll see some books would answer it in 2 separate problems. So square root of 10 over 2I comma, negative square root of 10 over 2I. Notice these are two separate answers, and when we answer it the first way here, what we're doing is just being a little bit lazy by using that plus minus symbol.